All right, let's get started. Welcome everybody to today's webinar of the Winning with 3D Experience Works simulation series. That's a town hall style webinar for CRE partners. So in this webinar series, it's a monthly enablement webinar series, which is exclusively for our CRE partners worldwide. The goal is to help you win with our 3D Experience Works simulation roles, which are all listed here. So you see here the role names, the role diagrams. We cover all the different physics domains, the structural designer, the structural roles, the durability, fluid dynamics, plastic injection molding, EMAC role, etc. So we have an overall of 10 sessions this year. We started in April, and it's for sales and tech sales folks from our CRE partners worldwide. So this is not a customer-facing webinar, and of course the goal of this webinar, or the key benefits for the attendees is to help you to learn how to discover and close sales opportunities, but of course also enhance your expertise in hands-on usage of our 3D Experience Works simulation with best practices and tips and tricks delivered by our simulator experts. So that's why we normally have a 10 to 15 minutes introduction from a sales expert from Dassault Systems. We'll talk about sales best practices, and afterwards we'll switch to our tech sales experts who explain the topic of today's session. Today with me I have Reza. Maybe Reza, you might want to introduce yourself.
So, yeah, good morning. Thank you very much, everybody, for joining. Special thanks to our presenters. I'm talking to you from the San Francisco Bay Area, Northern California. It's 7 o'clock in the morning here, and very much look forward to hosting with our great speakers today.
Yeah, so my name is Matthias. I'm located in Germany, so that's really a worldwide activity that we have here. We have also Ankur from India in the call, and Sagar and Todd from and Mark from NAM. So it's really international effort that we are doing here. And so the announcement of this 2023 webinar series you can find in the partners home community, and basically we have 3 webinar series. One of them is the partners only webinar series. That's the one we are in today. But there are 2 other webinar series running. One is about getting started with simulation on 3D Experience platform, and the other is ModSim with 3D Experience Works, which is more C-level information. So just be aware of that there are other 2 webinar series running, and these 2 are customer webinar series, customer-facing webinar series. Then you probably already have found the registration links to today's series, and the other series are also there. So once we have the recordings available, we switch from registration to recording, and then you find within these wiki posts the links to the recordings of the session, and can watch it again if you like. So today we are in October. We already have done a couple of webinars from April until September. So today's session is about material calibration and durability. And I'll hand it over to our presenters of today. So we have Ankur from the sales side, who is giving a sales view of our 2 topics of today. And we have Todd and Mark from tech sales with us. So I'll hand it over to Ankur. The stage is yours. You might want to introduce yourself, Ankur.
Thank you, Matthias, and good morning, all of you. In India, it is 7:30 p.m. So I assume most of the audience is in the daytime right now. So a very good morning for you. I'm Ankur. I'm part of the CRE team managing the simulation business from India. So let me start sharing my screen. Can somebody confirm when my screen is visible?
Yep.
Great. So as Matthias shared, that today's theme is step up your game with material calibration and durability. And what I would like to bring here is a view from the sales perspective. When I say sales perspective, it is basis what not probably what a technical person looks up to, but what a business owner looks up to, and what they like about the tool and what are these capabilities what we have on the table. So starting with the material calibration aspects of it, when we look at the material calibration and when we speak to a lot of customers and we show it to them, they gave certain reactions. So we have tried to capture all the reactions what we receive from people and the benefits what they see from this unique feature. The first thing is what is the current situation and challenges which people face with the material calibration situation is, as you all know, the simulation results are only as good as the quality of the material data input, no matter how sophisticated data we have received. But if you're not able to input the data in the right manner, it's not as good as people want it to be. Uh, One thing which stands out consistently is in the nonlinear space is creating material definition is considered as an expert domain, and it really scares design engineers. Many of them, because when we look at the 3D Experience Works portfolio, we say it's design centric, and anything and everything related to material is something what was considered to be too complex. So this is one area where people had challenges. Uh, Now, when in traditional systems, customer relied on material data received from lab test setup, which they still do, but then in the traditional methods, the data which comes from the lab, because it is physically tested, had a lot of noise and inconsistencies. The data was not very well fitted to in a standard curve. So it was not a very good data point for simulation, and people used to keep tweaking the data at all points. And it was also resulting in convergence issues. The data was received in Excel format, and it was not ensuring zero curve fitting, which became a challenge, as well as the decision about which material model to use and which material model to fit that data in is something which was to be decided entirely by the user. And if he's not an expert, they start getting hassles, or they start getting away from this activity. So the user have to decide, which is still a limitation in terms of effective usage. And the data which used to come is always a generic data format, and it used to require reformatting to match Abacus formats, and a lot of manual inputs used to go in. So this is where what customers have experienced the advantage of the material calibration app is. First is it's the interface that they love it, and it is so design friendly, and it aligns with our design centric approach. It's easy to see and easy to use, so even a designer who may not have too much of expertise would like to try it out without getting bothered about a very cluttered interface. uh, while using the material, this is one of the most important thing here is the material calibration app just does not extrapolates the data in the native format. It cleans up for noise and inconsistencies and creates much smoother curve, which takes the result towards better convergence, better accuracy, and overall better customer satisfaction. At the same time, while it is being done, basis the quality of the data which has come in and the parameters which it shows, the material, the app suggests suitable material models, so it reduces ambiguity due to user inexperience. So all in all, it becomes extremely convenient, easy, and powerful for people to get onto utilizing the material data in a much more effective and convenient manner, which can let more and more people adopt advanced simulations in a much convenient manner. So this is one thing, a few things what we have heard from the customer, and it is great for them. Now coming to the durability aspects is the question which keeps coming to everybody's mind. All the customers need an answer is how durable their product is. And when we look at it, almost every product failure for critical products and so not so critical products is caused by fatigue. And fatigue is something which will not show its impact right away. It will take a lot of time, and at some point of time the product fails, and people keep wondering why it happened. And because of all this, the challenge which also gets posed is, but empirical methods, people have been trying to do a manual extrapolation of the SN curve, and assuming that the maximum strain point or maximum stress point is a place where the real breakage will happen due to fatigue. But in all practical scenarios, it has not turned out to be true always. The breakage can happen at any point of time, any other place other than the point of maximum stress. So in this scenario, to overcome this, the durability rules which are powered by FESafe helps. And just for the audience information, FESafe was the first commercially available fatigue analysis software which focused on modern multi-axial strain-based fatigue model, and still it continues to set the benchmarks for fatigue analysis software. So it is one of the most respected and reputed fatigue analysis software worldwide, and now it being part of the durability roles on the 3DEXPERIENCE work simulation platform, it becomes even better. So when we look at it, few examples of fatigue is a bicycle usage, a bicycle pedal where there's a consistent load which keeps coming in and it breaks after a certain period of time. How is the design? The customers will be able to ascertain, will it last the number of cycles it is intended to last? And if not, they can do a deep dive, do design changes, do modifications, and run the whole test again, which would be a nightmare to do if they try to do in a physical environment, because physical environment needs those cycles to happen. And for those cycles to happen, that much time has to be invested. But that's not the case in durability roles. They can conduct any kind of life cycle analysis at a very, very short span of time. And not only mechanical, it finds implications in all the industries. If you look at the medical industry, hip implants, dental implants, we have seen examples of aerospace, we have seen examples of bicycle, we can see examples of train. Every industry has been using the fatigue solver from FESafe for any kind of durability assessments. So a few questions which keeps coming to our mind when it talks about why should anybody use a fatigue analysis software, because fatigue softwares are costly. Fatigue failures are costly and can result in accidents, or at least expensive products recall and warranty claims. We have been seeing recalls and we have been seeing warranty claims at all places. The traditional fatigue methods are time consuming and extremely unreliable, and hence a computer enabled fatigue analysis software is a definitive value addition. So the question is, everybody says even SolidWorks standard has a fatigue feature. Are all the fatigue software the same? No, they are not. In fact, many of our customers, just a second. Hello?
We can hear
You're
you,
good,
Ankur.
Ankur. We can hear you.
Sorry. So not all fatigue softwares are as accurate, because FESafe has that distinction in the market of being one of the most reputed, respected, and diversified fatigue analysis software. And the focus is realistic simulation, is not only to create some good colorful graphs and some vague predictions which people would know after a lot of time. FESafe focuses on not getting a wrong result and take the customer towards a very reliable lifespan calculations. And the question is, what is the fatigue life of any component? That's one critical question which keeps coming in, because that decides the kind of warranty the company can give to its customer, the kind of service planning they can do, the kind of MRO operations which can be conducted. Everything related to the product life cycle is determined with the fatigue life of respective components. So in all, FESafe is one of the most advanced, diversified fatigue solver, and which is now available as a durability role on the 3DEXPERIENCE work simulation platform. And I think it will be a great value add for all our sales engagements in winning against our competition. Thank you.
Thanks, Ankur. Thank you, Ankur. So with that, I think we will hand it over to, oops, my camera is not working, I think. We'll hand it over to Todd, and we'll start with more technical aspects on the material calibration app. So Todd, the stage is yours.
You can see my screen?
Yes.
Very good. Thank you very much. Yes, my name is Todd Dalrymple. Just by way of a little bit of an introduction, I'm an abacus-centric person, been part of the Simulia and before that Abacus organizations for a couple of decades now, probably longer than I want to admit to. I've held a variety of different roles, including very customer-centric roles here in the US in the past. And today I work for the R&D organization and am really the product manager for the material calibration app. And it's something kind of near and dear to my heart. I've always had a great interest in material modeling and in material calibration. So you can see the outline here. I'm just going to use a few slides, maybe 10, 11, 12 slides, getting everyone on the same page, and then the bulk of the presentation will be a live demo of the calibration app. Anytime I talk about the calibration app, I want to let people know about other resources that they have available to them. First and foremost, there's a very nice class or course on the calibration app. It's a 2-day course, and it's really filled with worked examples. I find that this app is very easy to learn, has some subtleties that examples really point out. So there is a class. And besides the class, I wanted to comment that if you were to use this link, and I'm just going to swing my browser into view here. So I'm now in the browser. I clicked on that link, and there's a whole series of posts in the Simulia community. This particular post serves almost like a table of contents. And if you were to scroll down, you would see this is all organized as a post of posts. So this hyperlink here would take you to another post that talks all about the calibration app. The links here talk about new features with every release, and you could just scroll down and see sort of the history of the releases, etc. And back here at this main post, if you scroll down to an area called sharing of material test data. So years ago, even before the calibration app was around, I started sharing some material test data with everyone to see whether we could all use that as examples to do calibration. If you clicked on that link, what you would see is, again, a post of posts sort of organization. It starts out with a hierarchy that says, well, we have some metals, a demonstration of the UHARD user subroutine, a bunch of aluminums, copper, solder, we can calibrate nitinol. And then if you were to click on any of these links, it would take you to another post. If there's a double asterisk in front of the name of the post, that just indicates that there is a narrated video there using the calibration app, okay? And a bunch of elastomers, quite a few elastomers, some foams, both elastomeric foams, crushable foams, some polymers and plastics, just one demonstration of doing a material calibration on composites, and something that's fairly new is a anisotropic hyperelasticity for some tissue. So I'll swing that out of the way and just say so that was my comment on resources, the course that's available for this app, and all of the things that are available in the Simulia community. So why calibration? You know, the really is that dating pretty far back, Abacus has had very nice advanced material models. I mean, again, the core of Abacus is nonlinear capabilities. Elastomers immediately get you into the nonlinear stress strain space. You know, metals past yield get you into the nonlinear stress strain space, etc. But for years, as I interacted with end Abacus users, they would say, well, you know, it's great that Abacus has all this technology, but I don't know how to calibrate those material models. And so dating back probably at least a decade, maybe close to 2 decades, I spent a good part of my time just making some calibration tools in Excel, helping put some calibration tools in Abacus CAE, et cetera. And so we started building this tool back in about 2018, and we do feel like in our very first release in the fall of 2018, we exceeded the capabilities that were available in Abacus CAE. And again, this is essentially enabling technology. It enables you to get to all the powerful things that exist within Abacus. So, the goal of the calibration app is simply to take some observed behavior, which for us is nominally stress, strain, time, test information, and to accurately come up with a math model that is a material model. And those math models are often driven by parameters, an underlying set of equations and some parameters. And the trick is to figure out what a good set of parameters is for any particular math model. We have been working now enough years that we have both constitutive models and some of the Abacus damage and failure models in the tool. And I'll make a few more comments about that in a few slides and during the demos. These last things here on this slide are some other ideas that we've had that are not things that we can currently do, but the fact is we understand that calibration could move outside of just constitutive models and have, for instance, the calibration of connector elements. We could even take very complex three-dimensional models and calibrate simpler models, sometimes models that we call abstractions. So that's just ideas for future things we should and could be able to do with tools like this. So this is just a little diagram that tells you a little bit about the history and where we're moving in the future as well. So level 1, this green level, back in, again, the fall of 2018 was our very first release, and we released coverage for hyperelastic, hyperfoam, and viscoelasticity, and we used what we called the analytical mode. And that analytical mode was that we rewrote all the equations for hyperelasticity and hyperfoams from scratch in C++, because we wanted to show that if we did that, we could have almost instantaneous calibrations. And we'll touch on this in the demo phase. But then after delivering that level 1 capability, we realized that if we were to continue along the path using analytical mode, it would take us quite a long time, and we would essentially be redoing work that was already done within the core of the Abacus software. And so in level 2, this yellow level, we said, well, let's use Abacus as a lightweight way of getting the stress response for any time and strain and set of parameters. So in 2019, in the fall of 2019, we released this version, and it opened up access to many Abacus material models, including UMATs. So we always intended to cover some of the user subroutines, material-related user subroutines. And we called this numerical mode. And numerical mode is still reasonably fast, but it's certainly significantly slower than using the analytical mode. And I'll talk again a little bit about that when we get into the demo phase. And this level 3, or purple color here on this slide, we had always intended to make sure that we got into some of the more challenging material models in Abacus, certainly the area where many users found it difficult to understand how to create a set of parameters for these damage and failure models especially. And we have delivered on several of damage and failure models, and we will continue to do so in the future. So again, I wanted to, in these slides, use the words analytical mode, numerical mode, and FE mode. So that last purple, the last purple, level 3, really says what the user is going to do is bring a run-ready finite element model to the app, where that finite element model fully represents the test that was performed. And the intention here is that there are quite a lot of tests where you don't have a homogeneous region of stress and strain that you're measuring, that there are stress and strain gradients within the measurement region of the test. And in fact, you might just use global measures of force and displacement to monitor the progress of that test. And one very simple example is indentation, like spherical indentation of a foam. Actually leads to quite a lot of gradients underneath the indenter. But another use case is the idea that you have failure or damage in your model. And as soon as you have failure or damage, you have in the measured region or in the active region of interest, you have quite a lot of gradients of stress and strain. So I won't read through this whole slide, but this was to have a little slide that just showed you that a sequence of events, and you can read down through this, but I'll talk a little bit more about this in the demo phase as well. But this FE mode really brings a tremendous amount of power to the calibration app. So I'll have a few slides here where I talk about release levels. We tend to release one major release a year and one minor release. These days, the major release is typically in the February-March timeframe of each year, and it's usually with an FD01 release. By now, we do not have complete coverage of all the Abacus material models, but we have, I guess, what I would think of as about 70 to 80% coverage. So you can see in this slide, if you looked at the material models available, and this is a rolled up view. If you unrolled this view, you come to this center image. And if you, for instance, were to say, I want to calibrate elastoplastic metal with rate dependence, you then get another screen where you get all the choices for the various kinds of hardening curves in classical metal plasticity, and including some additional feature for rate dependence. Another example is if you were to click on the elastic creep material model, you would get again another dialog box. It would give you all of the creep models that are available in Abacus. So with each major release, we definitely work on pushing the envelope for the material model support, because we would like to have perhaps not 100%, but near 100% coverage of what users would like to use within the nonlinear space. Another area that we work on quite a bit with every release is the whole idea of test data processing. So the image on this slide shows you some of in the upper part of this image is all sorts of activities when you take test data and want to clean it up. You might want to decimate it because you might get thousands or tens of thousands of data points from a test lab, and you really don't need those many points, and those number of points can hurt the performance. So we have decimation and regularization tools. We have smoothing tools. We have some ways that you can identify critical points not to smooth over, and we have a zero shifting tool, because oftentimes there's a little bit of slack or preload in your experiment. And again, the class that we offer on this app gets into quite a lot of detail of the test data processing, and there are some posts on the Simulia community that get into that as well. Just to point out some things that we've done fairly recently. This slide, and I'll let you read down through all the details. Valanis Landell is another recent addition to Abacus for hyperelasticity. Traction separation is a material model that's used with adhesives. So we have some coverage for the failure of adhesives, which is pretty important to lots of industries these days. It's always been very important to all the electronics people because so many phones and other devices are put together with adhesives, but more and more, even larger objects like automobiles are put together with adhesives. a customer request for a couple of years had been the idea of comparing multiple material calibrations, and so we added that capability in this last spring, and then we also added this idea that you could create a master curve for a Prony series material model, and that's the image here is just showing a bunch of test data all knitted together into a master curve. Though I'm near the end of the slides, and this is really just a whole litany of some fairly advanced features that we've put in the last little bit. If you see something here that says 24x FD01, that is a major release that should come out to the public in the February, I think early February of 2024. So still a few months out. And my last slide is some other things. And again, I don't want to really get into the details of this, but just to see that the idea that we continue to work on both the test data pre-processing as well as continue to work on support of many of the advanced Abacus material models. I do have a slide here that if you got a copy of these slides, you could click on these links, and those links take you to the Simulia community. I'm going to go ahead and switch gears and do a live demo at this point. And so I've switched to a live demo. I'm showing you now the 3DEXPERIENCE platform. I'm using a public cloud. I happen to sit in the state of Michigan, and the cloud is somewhere, it's in Boston. I'm going to go to the compass, and I'm going to click on the material calibration app. You see up in the upper left that you're in the material calibration app. And I tend to use the icons in a left-right way. This is the icon that would choose analytical mode or numerical mode or finite element mode or FE mode. And what I want to do initially here is just do a fairly quick example. It's going to be in numerical mode. Maybe I'll back up for just a minute and say, if you were in analytical mode and you clicked on the thing that chooses your material model, you would find that there are relatively few material models. That again, the analytical mode is very fast. We rewrote all the equations in C++ to make it really fast. And if you're calibrating any of these material models, you'd want to use analytical mode. But I'm going to start my demonstration with numerical mode, and I'm going to go in and I'm going to read in some test data that comes from Excel, and it's from a 1045 steel. If you have multiple worksheets in Excel, they'll show up here. There's only one worksheet in this Excel file, and I'm simply going to say, and it's okay that I have some text. The tool is smart enough to just start reading when it sees the non-text, alpha characters. So we'll say next. I do have to tell the tool what is in each column. And if I've forgotten, I might go back and remind myself it's time, nominal strain, nominal stress. So time, and this is left over by the fact that that I had used this previously. And we give you a little preview just so maybe you might notice that you've opened the wrong file or something. So I can say, now that I'm happy with the columns that I've chosen, I can say next. I can supply a temperature if I want to, and I can say import, and I'll say close. So I've imported some data. We have a lot of graphical control. I want to make sure I'm plotting nominal strain, nominal stress, and I'll come back to that plotting a little bit later. So this is a pretty simple example. There's just one piece of test data. We do allow as many pieces of test data as you would want as a user. I'm going to go and choose my material model. My material model is this elastic plastic, metals. And the metals just means that it's a Mises yield surface. So I say, okay, And then this area of the screen populates with, again, all the different choices, the more detailed choices that one could have with these material models. It defaults to the isotropic Johnson-Cook, which is, we feel, is heavily underused by our customers. We think that the Johnson-Cook is a very good material model for a variety of reasons, and people underuse it because they don't have the calibration tools for it. So we have some heuristics. I'm going to just change the response line to black, have it stand out a little bit more. So this is, in fact, data points. The red are data points, and the black line is a response line. And I did want to mention one thing, that if I want to calibrate this bit of test data for a 1045 steel, I really should not be using the data that's past ultimate, unless I use finite element mode so that I can capture the necking that is present in that phase of the testing. So I'm going to double left click on the data in the spec tree, and I'm simply going to make a quick estimate of where ultimate occurs, and I'm simply going to say delete, say OK, and now this is really a much more valid piece of test data for the calibration that I'm doing right now. Again, we could have done a more advanced calibration of things past necking, and there are similar community posts on that. So I've changed to numerical mode. I've read in some test data. I'm not going to talk about this icon here in the demo, but this icon is used so that you can see deformations other than what you have represented in your test data. I've chosen my material model. It automatically gives me this black response line, which is the response to the set of parameters that we're using. And as a user of this tool, we have some heuristics that looks at the test data and gets a calculation of the Young's modulus. And in this case, it looks very good. And I can just say, if I uncheck the E, the Young's modulus value, that unchecking says, don't keep this held fixed, don't make it a design variable. And I tend to use words like design variable because this is an optimization-based technology. So when I go to calibrate, I start to invoke an optimizer, and that optimizer tries to get this black response line, math model response line, as close to the data as possible. And as long as this is already such a good Young's modulus, I'll just turn it off as a design variable, and I'll be left with 3 design variables that are part of the yield curve or hardening curve. I could change any of these by hand if I wanted to. For instance, this 480, there is some heuristics that looks at the test data and makes this initial calculation. I could set it to something different, like let's delete that, and then change this to be say 300. And all I really wanted to do is show you that we immediately recalculate the response curve, the black line, though my choice of 300 is actually worse than what was calculated to begin with. And if I want to get back to that initial calculation, I can just simply click reset. Okay, so that gets me back to the software provided initial parameters. And at this point, I'll again uncheck that as a design variable, and I'll just go ahead and run a calibration. So this calibration, numerical mode, is going to take longer than analytical modes. It's still not going to be terribly long, on the order of 5 or 6 seconds. We were going out and getting our stress response from Abacus Standard at this point. And you can see the shape of the curve. You can see the error norm. Again, this idea of an objective history, that's all language that comes straight out of the optimization world. We do have a lot of advanced features to control the optimization, but we tried to make the tool such that a part-time user or a novice user doesn't really have to pay too much attention to that. I'm going to do another example that's, we teach a class in elastomers, and this is data from that class, and I've already read it in just to save a little bit of time in this demonstration. So this little abbreviations that I use in the legend, the red is some simple tension or uniaxial test. The blue is, the EB stands for equal biaxial tension, and the PT, the green line, is planar tension, and this separate graph is the volumetric or hydrostatic pressure volume ratio testing of the material. And one thing that I just wanted to quickly show you is that there are many, many data points here in the volumetric. And one thing I could do is left click on the volumetric data and come in and decimate the data. And it's got a total of 245 points. I'm going to decimate it down to about 40, say evaluate. So that's my new set of data. If I commit to that data and then say OK, it has decimated the data. So I just want to do a quick demonstration of one of the various tools that we have for cleaning up your test data. So I'm going to go in and just choose, well, hang on just a second. Before I do that, I'm going to move back to analytical mode, because hyperelasticity is one of the choices here. And I'm just going to choose hyperelastic. We have some modifiers like hyperelastic, viscoelastic, and we have the capability to include Mullen's effect. When we choose that, we get all of the hyperelasticity that's available within Abacus. And I'm just going to, for the moment, choose a Yo model. And I'm going to, you can see we already supply you some initial parameters. We show what the math model response to those parameters are, and the thing I wanted to show, I guess I'll just jump in. We can modify any of these parameters by hand, but I can just go ahead and calibrate. I'm apparently running into some issue there with my calibration of this material model. It's a little surprising. That's always a challenge with doing a live demo, is ending up with some gremlin creeping into things. But I'll have to go back and deal with that on offline a bit. So the last demonstration that I wanted to show is also in analytical mode, or numerical mode is a superset of analytical. This shows you that I'm in an analytical mode. This butyl rubber test data is out on the Simulia community. There is a post about this on the community. I've read in all this data, and it's a test on butyl rubber at 5 different rates. So the green is the lowest rate, the red is the fastest rate, and the rate is shown here in the legend. I was looking at some of the questions, and I guess I should go ahead and take some of the questions. ANSYS Mechanical has material calibration. How is our tool superior to theirs? I personally have not used their tool, so I really can't speak to that all that well. What I can tell you is we have paid a lot of attention to details, like the idea that when you click on a material model, and here when I choose a material model for this butyl rubber, it's going to be a hyperelastic, viscoelastic model. And we've really paid a lot of attention to the user interface and making it very easy to use. But again, we want a novice or part-time user to have this be an easy to use tool. For instance, one thing I have not even shown you yet is the idea that we have lots of optimization controls, and that's this icon right here. We have not only multiple error norms, but we have multiple optimization algorithms, and yet we want to keep. Many users don't want to dive down into that level of complexity. Many very advanced users do want to drop down into that. In fact, they want to see that kind of level of technology. So I would say that that is something we've paid a lot of attention to the details. Do we have recommended material labs for customers? I myself live in the state of Michigan in the United States, and I personally and some of the people from the local Samulia office have a good relationship with a test lab here in Michigan called Axle Products, which I'm happy to recommend. There are several other, and again, I'm familiar with things in the US. There are several other, we could maybe just address, answer that after things are over, but I have several other test labs that I would be happy to recommend as well. So again, looking at this, I'm going to change this from a Neohook to Yo, and so we have here, this part is the elastic part of the response. This part down here is called the Prony series viscoelasticity, which is a linear viscoelasticity. Again, this tool has lots of plotting options. One thing that I can do is I can come in here, right click, say duplicate. That duplicates this plot. I'm going to show it. And then I want to look at the data in just a slightly different way. Instead of looking at it as a stress strain, I want to look at it in stress time and show it on a log scale. When you're looking at viscous behaviors in materials, you often want to understand how they behave across time as well as how they behave across stress strain. So it's nice to be able to plot both of these simultaneously. And when you're dealing with Prony series, there's a rule of thumb that many practitioners would know, that you want to look at the span of time in your test data and pick about that many decades of Prony G and tau pairs. And the tool has some heuristics. The tool did go look at the range of the test data and picked 4 Prony G and tau pairs. I'm actually going to increase that to 5 using my own preferences. And what you'll see here is, again, we have built in a lot of best practices into the tool. Taus are not terribly important for the exact value of the tau. It's important that you have about 1 tau per decade of time. And so we have chosen to turn them off as design variables, and you can use this little filter. So the filter will show you just the active design variables, or the parameters are going to change during optimization. We can look at this, and we do populate the initial values for you, but a user could look at this and say, well, this red solid curve, which is the math model response, wants to match the data, and the green one wants to match this data, and I can better match that data just by changing from 0.5 to 5 megapascals, and you'll see all the curves kind of jump up. And what's important here is, especially in the small strain region, right down in here, the red curve matches much better. And again, I'm going to type in some other rules of thumb that practitioners might know about, and that is to set C20 to some small negative value, and maybe even set C30 to some other value. Setting those other values wasn't too important, but I wanted to show you that the user can, if the user wants to, the user can change all of these values. And now I'm just going to go ahead and run a calibration. So there, my calibration happened in under 1 second, and you can see the elapsed calibration time is very small. The calibration happened almost instantaneously, and we show you the responses both in this plot and in this plot. You can look at the parameters. You can look at the R. We happen to be using an R-squared error norm with this, and the R-squared error norms for each of the pieces of test data is 9.8 and 9.9, and even better than 0.99. So I think with that, I will go ahead and say that that's a good stopping point. If you want to see for instance, this butyl, a narrated video of this butyl calibration. You could look on the Simulia community. The elastomer class 1 is also on the community. There are a lot of different material models covered there. So again, I talked about the test labs. Besides Axle Products in Michigan, there's one in the there's one that's called Data Point Labs. If you just did a Google search on Data Point Labs, a good number of customers use Data Point Labs, and there are a few other labs in the U.S. that I'm aware of. Another question came in: do we know which percentage of our customers use material calibration? Well, I don't really have a firm number on that. I can tell you that I interact with lots of customers directly that use the tool. They tend, the people that I interact with tend to be using some fairly advanced material models, like the parallel rheological framework model, which is a model that can be used for either elastomers or polymers. I would say that within the electronics industry, because they're dealing with polymers and elastomers and adhesives, there's quite a good percentage. I would just take a stab at maybe saying that in the electronics industry, probably 50% or more are using the material calibration app. In other industries, I'm less sure. So with that, I guess I would say that this segment of the presentation is over. And if you have any further questions you'd like to ask, please feel free. And if not, maybe maybe we should move on to Mark Pickering's presentation.
That was great information, Todd. Thank you so much. Just for the information of the audience, I posted the link to the first the calibration app new features in 2023 in the chat. And if attendees go there, obviously, you can kind of go to different locations. I just encourage you to kind of go there. Todd and colleagues, they post very useful information there, a wealth of information that you should take advantage of. Just one question, Todd, you mentioned about that 2-day course that, again, I'm sure it's extremely kind of beneficial. These courses, are they offered on a regular basis, or kind of is it kind of on demand that the date is not really clear and time to time you make it available?
Well, there are some online. The class that's specifically made for the calibration app is available online, so you can just go to it and listen to an e-course, if you will. Okay, and there are other classes that touch on the calibration app, but are specific to certain material classes. We hold a class in a test lab. We generally taught by an instructor and talk about the testing aspects of things as well as the calibration aspect of things, very specific to elastomers. That class, again, I think COVID has put quite a hit on doing things in person. That class is generally scheduled for once in the spring, once in the fall of each year, but there was one scheduled for October, and it did not go because there were not enough signups. So yeah, we have a variety of classes that are specific to certain kinds of materials, and there's a class on metals, there's a class on composites, there's a class on geotechnical materials, and we would like to, over time, push some amount of content of the calibration app into those classes where it makes sense, and we're partway into that process.
Fantastic.
Just one further comment before we switch to Mark. You might ask yourself which of the rows contain the material calibration app, and I just wanted to put this slide in here that shows that all the rows that contain our mechanical scenario creation app also contain the material calibration. That means we have the material calibration in our structural mechanics engineer role, the SSU role, as well as in the durability and mechanics engineer role, the FGM OC role.
Thank you.
So now we can hand over to Mark.
Okay, well, hello everybody. Let me see if I can just get this sharing. So hopefully you're seeing a slide.
Yep.
Yes.
Perfect. Well, thank you everybody. So basically in this bit, I just want to go over essentially three main aspects. The first aspect was sort of touched upon already by Ankur, which is why fatigue? Why should we be paying attention to this? The second aspect is going to be a little bit on, okay, fatigue is important. How do we actually do that in the program? And is this a really complicated thing or not? And then the third aspect is something that wasn't previously in the 3DEXPERIENCE Works portfolio, but has been now for a couple of FD releases, which is weld fatigue. And the fact that that is actually a little bit different and needs a slightly different approach, but in terms of the usage is not actually that much more complicated. So with that, let's see if we can go ahead. And basically this is sort of another variation of what was presented earlier. This particular one was an NIST study of failures, and they looked at 230 of them. And the sort of things that you would typically address by Abacus or FEA in general, so we got wear or overload, accounted for about 25% of those failures that they were looking at. But fatigue was about 60% of the failures within here. So that, along with sort of the things that Ankur showed, it's like, yeah. And I kind of feel like this is one of those things where, because FEA has become fairly mainstream, that means a lot of things get looked at with FEA. And if you start looking at them, you just start having less problems because you're resolving those issues in the analysis beforehand. Fatigue is not as widely adopted as FEA. And so that tends to mean that it just gets ignored a little bit. But then that doesn't mean that it won't actually occur. And in reality, we do end up. And so that tends to skew the numbers up a little bit here for this. But one of the main examples that I use, and if you've seen me talking about fatigue before, you'll have seen me talking about this one. It is now quite old. This was actually done back in 2010 and presented at the Safe User Group meeting. But it very clearly shows to me where FEA has problems when it comes to addressing fatigue damage. So in this particular one, it's from Hyundai, and they're looking at a steering arm, and they've basically got on the left here, let me see here. On the left here, we've got the steering arm, we've got a pneumatic piston here, or a hydraulic piston. We're pushing on this end of it, and then we have mounted it down to this block over here. And then we have a finite element model of this situation set up as well. And what they're going to do is a couple of things. So they're going to do low-level fatigue loading, and then look at what happens. So we've got plus 600 to minus 600 cycling on the end of there. And then we've got the practical test that they do, and it fails around these mounting blocks. And this is actually an FE safe analysis, but you could do this from FEA. So I don't want to give the impression that you can't address anything fatigue from FEA. You can, you just need to be aware that you're not addressing everything. But you could look at this. You could go in here, you could find the stresses here, just compare them to an SN curve, predict a number of cycles. And indeed, in finite element analysis, I see a lot of this proxying. We have a fatigue life. We can't calculate fatigue life from FEA, so we'll proxy in a stress limit and just say, okay, so long as your load cases are below the stress limit, you're good. And this would actually work for this case. The high-level fatigue loading, so we go up to plus 1960 and then minus 600. So this might be something like hitting a curb strike or something like that, pothole. When they do the test, once again, it fails around the mounting blocks. And again, from FE Safe, but also just from stress analysis, you could probably predict this failure location around the mounting blocks. So far, so good. But obviously, this would not be a paper in a durability software conference if that was the end of the situation. So what they're looking at now is, okay, what happens if we have one hit of this pothole, but then we're doing regular driving after that? So we're not hitting a pothole all the time, but it does happen. We're not, and that's what's happened. And they knew from testing that this is the failure they would get. And this is typically the kind of thing where I see fatigue become a mainstream use of something. So typically I see FEA become a mainstream use because there's something like this. You can't hand calculate what the stress level is. And so then to get a bit more information about it, you then start doing FEA that gives you more fidelity on the model. But then you would go through, and if you were predicting this from an FEA perspective, you would say this load case fails at the mounted bolts because the component load cases fail there as well. But practically, they know that it doesn't. And so you need something that can account for the damage accumulation and the relocation of this failure location. And then obviously, because this is a safe technology paper that was presented as a safe user group, FE Safe can indeed capture this change in location, and the lowest life is then in the arm for this case. So that really is sort of the main thing. If you're only going to take one takeaway from this bit of the section, that would be the thing I would like you to take away is FEA can address sort of fatigue problems, but it doesn't address all the mechanisms that are there. So that leaves you open to actually having fatigue problems in the real world, even if you analyze it up front. And that's kind of what we saw with the NIST study and the other information presented is a lot of actual failures that take place are fatigue failures, even on things which have been FEA, because FEA focuses on a failure mechanism that is more appropriate for something like an overload case or something along those lines. And we do indeed have software that can address this. And then once people start addressing this, then they start realizing there's all these interactions going on between things, and it tends to become a mainstream application for them. I'll skip that next bit. So yeah, so what I wanted to do now is look into a little bit about, okay, in the program, how do we do fatigue analysis? And so in here, I've just got this sort of bike. You'll see there's some blue lines and some red lines. These are just, this is a shell model only. So it shells all the way around everywhere. The red lines are denoting where we've got a compatible mesh for the weld. And the blue lines are where we're denoting we've got an incompatible mesh. This is, for those of you who are familiar with it, the line fastener technology that's in 3DEXPERIENCE. These are easier to set up. And in here, I'm saying, well, these are the critical locations. These are the welds that I'm interested in. So those are the ones that I want to look at. And if I swap into the unit load case, we can see that basically all I'm doing is saying, okay, we've got a push load in X, we've got a push load in Y, we've got a push load in Z. So that is our core load cases. But then when I want to come in and do the fatigue analysis, I basically, you'll be familiar with this, hopefully, that you'd create your analysis case. This is how you do the FEA, loads, boundary conditions, etc. If you have a role which gives you durability, you'll see it's not a separate app. It's just a tab on here. And then you can create the durability case. You can do FKM. I'm going to ignore FKM here, just because I'm not as familiar with it. But you could do FKM durability analysis as well. But in here, the main things you would set up is the global surface finish. So this is just the basically how smooth a finish do you have. Durability test specimens usually are mirror polished, but then the roughness of that will degrade the fatigue life in comparison to that test specimen. So just choose whatever you're going to choose here. And then you can have a local surface finish as well, so not really applicable here, but let's say the inside of these bores was finely machined. You could set that up so that they've got a better fatigue life. But then the practical part is going to come in from this fatigue loading. And what we're doing here, you can see that we've got basically two choices. You could do a sequence of frames where if you've got like push forwards, push to the right, push to the left, push back, push down, all as like a flip book or a set of analyses, you could sequence them together. But in here, what I'm doing is a superposition where I say, okay, let's look at that X loading and give it a cycle where it's going 0 to 1 to 0 to -1. So a straightforward sinusoidal cycle. At the same time, we'll be doing Y, which will go to 2 times as much and cycle, but out of phase. And then for Z, we'll push to the right and then we'll push to the left. So we cycle sinusoidally between those as well. So this is really the most difficult part from a user perspective is for fatigue analysis, you need to have a cycle that is going through that is then repeated and just setting that cycle up. But once you've set it up, this is all you need to do. And then you can go straight into the results, hopefully. And we'll come back out. So here I'm looking at the base metal fatigue, and now we're calculating out. These bits here show obviously the worst life, but they're not the things that I'm actually focused on, because we're going to try and get into the weld fatigue later. So we're interested around this top area. But what we've done here is we've just said the material has got a particular fatigue curve on it, and we run through and we do anything, and that's all we set up in the durability case. So in terms of usage, there's not a lot of complexity here. The complexity is defining that fatigue loading, but you can just use the properties that are in the material editor to actually define all of the complexity of the maths behind it. And fortunately, if you have got a role on 3DEXPERIENCE which has a durability capability, you can also download a material library where there is already a wide variety of metal materials with appropriate properties set up for the different algorithms that are being used in the background. Now that's the first part that I want to get to is, okay, it's not actually that difficult to set up. But then where I wanted to look at this and where I do see people getting into a bit of trouble is these welds. So the welds in here, we have just at this stage assessed them as if they are parent plate, aluminium material or steel material in this case, and just run through. And we've done some calculations, and yeah, we can see there's a little bit of a hot spot here. But if I actually go over to the Verity approach, we can see that for the same loading, the same history, the welds themselves actually have a notably lower life. And so we need to address this in a slightly different fashion. And that's what this Verity case is. So if I go back to the scenario, what did I do for the Verity case? Well, if I open it up, we've still got the same thing. We've still got the global surface finish. And indeed, what I did here was I just duplicated the base metal fatigue case. And then So that gives me the load history, gives me the output requests, everything else. It then gives me this interaction where I can just go through and say, I want to add a weld fillet set. And in here, this was that why I kind of mentioned at the beginning the difference between the blue curves. If we zoom in here, you'll see that for these, so if I zoom in here, you'll see that for these blue curves, they're in what is incompatible line fastener approach, which basically means we'll create these pinkish elements, but they will be completely disconnected. There will just be a row of elements. And then what we will do is we'll use these couplings to connect together the edges of these pink elements to the edges of the elements, or to the underlying elements on the main shaft here and on the main collar. So there's no direct connectivity of the mesh. If I'm using this weld fillet set, then by default, if we've gone in and we've said, actually, I've got a compatible weld, and in here, up, let's do a clipping box. Showing it up nicely, sort of. Okay, so if I zoom in again here, okay, that's better. We can see we've got our main tube, we've got our sleeve tube, and then we have created this line fastener here where we have got full connectivity between these. And I also have this weld coming down, which is the main connection, and then also this inclined weld shape to give me the sort of profile of a lap joint weld here. But because this is in compatible mode, that is a direct element node, element connection going across here. But where was I? I was talking about the scenario. So in here, yeah, if I go in, I can just go into durability, say the weld fillet set, and then basically go into my finite element model, find those compatible line fasteners, and then just add them all in here. There are various options if you want to play about with this, but the main ones that you would practically do is, are you doing a steel weld or an aluminium weld? And then are you looking at the mean deviation or the mean life or one of the standard deviations away from that life? So 50% chance of failure, 2.2, 0.12%. There are some other bits. So one of the things you might be familiar with from welds is there's a lot of different locations where they can fail, at the toe, in the throat, from the attachment, etc., etc. By default, this will just look at the toe failures, which is why when we went to the results, we saw a band of results on this side and a band of results on this side, because those were the way the toe failure calculations are being done and shown on these elements that are there. But really, that is it. To go into doing a fatigue analysis of a weld, the only additional complexity you've got to do is set up a weld fillet set. And if you've set this up as a compatible line fastener type, it will pick that up straight away, the support boundary type where you can put the inclined weld in. There is also a weld line set where you can go in and define actually sort of a line of elements that will be your weld. But for what I would just sort of suggest here is just use the weld fillet set and use the line fasteners that you've created. So the bit that I've not really explained here is why was that weld worse? The usability of the weld and putting it into the calculation is fairly straightforward. I will just note, actually, given what was mentioned earlier, the weld fillet that is, or the weld analysis capability for durability is only in cases where you have the mechanical scenario and then the durability. If you have structural scenario and then durability, you can only do the base metal fatigue, which is basically this area. But to get to this weld fillet set and get to the verity calculations that are going on in the background, you do need mechanical scenario. So that's just something to be aware of, which is, I believe, the FGM, I think, is the one which has mechanical scenario, the SSU with durability. But if I go back to the presentation, skip these bits, skip those. Okay, so this bit's interesting. Yeah, actually, I will go into this. So one of the things that I do see a lot of is people often think of durability just because it's not as mainstream as FEA. They tend to think of it as a new technology, something that we're just exploring. So what I wanted to point out here was basically a brief timeline of modern FEA. And it actually comes in 1960 is where finite element method gets sort of first referenced as a discrete thing. 959 to 64, this actually isn't FEA, this is basically CAD. But then fairly shortly after that, we get NASTRAN, the NASA Structure Analysis Code. And then 10 years after that, 1978, we're getting Abacus. And things that we would recognize today as modern mainstream FEA is basically 70s technology. And I would recommend this if you're interested in the history of Abacus. There is a CCMEI Distinguished Speaker Series that's on YouTube where David Hibbert is talking about the early days of Abacus and what they did and how they founded it. And that is an interesting watch. So a bit of a distraction, but that is there. But when we come to fatigue, really the first concepts of fatigue were brought about in the 1830s with Albert, where he's looking at chains for mine usage. The drawback of this is he's looking at a chain. So that's kind of the scale that he's looking at. In the 1860s, Waller starts looking at fatigue failures on railway axles. And this probably most people will recognize who are doing fatigue even today as the SN curve. And that kind of concept is well over 100 years old. And this is kind of the approach that's already in SolidWorks simulation and looking for fatigue. Look at the stress. So you're looking at a macroscopic scale, but of a region of the model. So instead of a chain, we're looking at an axle, but we're not looking at an axle. We're looking at a stress region on the axle, and then what failure will occur from there. And then FE Safe did come about in the sort of so I think basically in the 1990s, FE Safe comes onto the market, and it is commercializing what is multi-axial strain-based approaches. The main thing I want to take away here is that these concepts were around in academia from the 1960s. So even this, as like the most modern generation of it, is basically the same kind of age as FEA. So it's not a brand new technology that we're still experiencing. It is a well-known, well-understood approach. It just doesn't happen to have gotten the mainstream approach. But what's nice about this is that it actually enhances this stress-based approach, looking at a crack tip and looking at the micro scale sort of ideas to get the plastic straining at the crack tip and then incorporating that. And where this really comes in is instead of looking at these very high cycle fatigue of railway axles, you're now pushing back to lower cycle fatigue failures, where the plastic strain at the tip tends to start dominating the fatigue damage that is accumulating. But the bit that I was really trying to get to was welds. And welding is bad for a variety of reasons, but there are unfortunately very famous cases. This particular one that I'm looking at here is the Alexander L. Kyland. And this is a Norwegian drilling rig that did unfortunately collapse in 1980, and there was life lost on that accident. But the root cause of this was a weld on this member that held a small sonar type device on there. And this is a mining rig or an oil drilling rig. So this is a huge, huge structure. But what brought it down was just a small weld that wasn't even a load-bearing weld. So why was that? Well, it's basically for three reasons. And this is just a chart showing the poor life of welds versus even notched specimens of parent plate. But why do welds have such bad fatigue life? And there's basically three problems, or at least the way I'd like to break it down, three problems. The first is geometry. Whenever you put a weld in, you will automatically have a sharp corner. Typically, if this wasn't welded together, there would be a fillet in here to smooth that out. But there's no real, with a weld, you just get a sharp corner because you get this sharp re-entrant corner. There's then also a residual stress effect, which means that when you weld it up, you're melting the material and then it cools down. And so there's a residual tensile stress there, pulling, particularly at the weld toe. And what that means is that in base metal fatigue, if you've got reversing cycles like compression in your load history, that typically is not considered damaging. But when you superimpose that on a residual yield level tensile stress, even the compressive cycles become damaging because you're cycling a fully tensile state. So that's again another reason why welds are bad. And then the final reason is that just by welding something up, you actually introduce a small crack. And the majority of life in base metal fatigue is actually creating the crack. Once you've got the crack, growing the crack tends to be fairly short. But welds are bad because they always have a crack. At least conceptually, they always have a crack. So that life of generating the crack is not there. And it also leads to this kind of thing, which shows a difference between welded structures. With base metal fatigue, you can increase the fatigue life of it by increasing the material grade. Basically, the higher a UTS, the harder it is for that first crack to generate. And so you get an improvement in life. But if you're taking that aspect away because you're welding it, then increasing the material grade of your steel hasn't influenced anything at all because it's just the crack propagation stage. The last couple of bits I'll take on is different approaches. So welds have been known for a long time to be bad for fatigue. This is kind of the classical way, and certainly the way that I certainly learned how to do weld fatigue, is people have done tests and worked out what the nominal stress would be and what the actual failure is of particular types of attachments on simple specimens. And they basically grouped it into different classifications of weld. And then what you as a user would do is you'd say, okay, my particular structure at this weld looks kind of like this setup. And so because it looks like this setup, I will choose this curve, and then I will do my calculations based on that curve. That was a problem for a couple of reasons. One of the reasons is this is often a nominal stress case. Think about like a 4-point bending where you've got a constant stress region. You nominally know that, you put a small attachment on and you weld it, and you really looking at your calculation of this stress strain curve or this stress life curve from that nominal stress. But in FEA, we always get the local stress. So determining what is the same nominal stress as the on your generic structure you're looking at can be difficult and lead to interpretation. And as well, you also have to choose which curve is most appropriate. And often these will be in line with the loading or perpendicular to the loading. But on a practical case, things will tend to be at 60 degrees or 40 degrees or 30 degrees from the loading. So what do you choose? And that's why generally in 3DEXPERIENCE, we've put in the Verity approach. This changes things up in the background, but like we saw from the example, you don't need to necessarily worry about this. But the main thing it brings out is because it's looking at this structural stress, which is based upon the forces across the cross-section of the attachments, that tends to collapse all of these different curves that we saw here into a single curve. And so that's why we no longer need to interpret things for Verity. We can just say it's a steel weld or it's aluminium weld, and we just have a single curve here, and then we can go ahead and do that. So that's all I really wanted to say. Durability is important. It is very practically the case of a lot of failures. It is not terribly difficult to put into here. As long as you can define your cycle, your fatigue loading, then the program will resolve a lot of decisions that are taken just because they are in here inside the material choices within the durability of the material itself. So things like what fatigue algorithm to use, etc., etc. If you just take the defaults that come in the library, great. That's all you need to do is set it up. And then for doing welds, again, there is a lot of complexity. Using base metal fatigue algorithms on welds can be done, but doesn't really account for all the damage that's been incurred there. But for Verity, all you need to do is then just choose the weld fillet set, where you then go back in and say, okay, these are my line fasteners that I made. They're the ones I want to do. And it will do all the calculations for weld toe failure, etc., etc. But that's all I had.
All right, Mark, thanks a lot. We have one question that came in. Can you please compare FESafe and ENCODE?
So yeah, so that's a sort of fairly common question. ENCODE was kind of the code which really became the mainstream durability analysis for a lot of people for a long time. It was focused on stress-based approaches, so kind of links into that Waller SN curve, looking at railway axles where you're looking at millions of cycles. FESafe really was the one that pushed into the multi-axial, so damage in different directions, accumulating on a critical plane is kind of the thing that FESafe first brought to the market of commercial use out of academic use, as well as strain-based approach. I believe ENCODE now has adopted a strain-based approach as well. But I can't really comment on how good it is or how accurate. We do know from our users in FESafe, we got into a little bit here of some examples afterwards, that FESafe and its approach tends to be pretty good. So here we've got one where we've got who was this? Yamaha were doing a 400,000 cycles. Predicted life of 366,000 cycles. And then we've got another one here with a trailing arm link where they had 0.83 repeats of their block cycle test and 0.81. So this one I think was Ford. Yeah, Ford. I think overall there probably is some technical differences between them. My main perspective would be think about durability and think about fatigue. And then the fact that it's all together for you in 3DEXPERIENCE. You don't need to swap out to another code. You're just in a durability tab, and then you're just putting in, and by default, it is multi-axial strain-based approach. And even if you need to put in wells, you just go in and say, okay, these line fasteners that I connected everything together with, those will be where I need to calculate it, and it resolves that and picks it all up. I can't really comment on how smooth a user experience encode is, but this to me seems a fairly smooth user experience in 3DEXPERIENCE.
All right. Thank you,
Mark, you mentioned about compatible versus incompatible line fasteners. Any recommendation in terms of preference and accuracy?
Well, that was kind of why in this case here, I did break this down. Is these are easier to generate, they're quicker and faster. In here, as an example, I would say that the Verity approach, being based upon the structural stress, based upon the forces across the joint, does kind of conceptually rely on you having modeled the weld and you having a compatible connection between there. But this does require more model building limitations, as in you have to make a compatible weld. This is kind of what I would do is, if you're doing a structure, don't worry about the welds where you're not interested or not your design focus. Yeah, an incompatible line fastener is fine. You just need a connectivity. You need a load path across them. Great. If you can, where you are doing a weld analysis, a fatigue analysis, do put in the extra effort to try and make sure you have got a compatible weld there. If it comes out and if that is just too much of a modeling requirement, then yeah, you can do this and you can get answers based on an incompatible approach, using the weld line set instead. But as we can see as we zoom in, because you're smearing that load across the adjacent elements, my general recommendation would be to have a fairly fine mesh there if you're going to use this. It's a little bit more complicated to set up in the program because you do a weld line instead of a weld fillet set. But if for some reason you can't generate a compatible line fastener, or you can't generate a compatible solid mesh, or a manually create compatible line connection, you can still do calculations here. I would recommend, though, paying attention to mesh density and making sure that is a fine meshed region, because it is going to smear things out a little bit. And again, an A-B-like comparison would be good. So if this is design one that we know is out there in the market and works, and then we've got a new concept for a new connection, then we would look at that, but we would compare back to design A. But in general, compatible is kind of the concept. You can do incompatible at a push. Just use it at your own risk.
All right, we're slightly over time. Are there any more questions? Let's give it 3 seconds. Okay, if not, just give me a chance to share my screen again, because I would like to repeat again which of the roles. Can you see my screen?
Yes.
Yeah, which of the roles contain which of the fatigue capability. So that's what Mark mentioned. Whatever role contains, or whatever of the two durability roles contains the structure scenario creation app, contains the base metal fatigue only, and the one with the mechanical scenario creation app, which is based on the structural mechanics engineer role. This one contains also the capability to create a durability case, but in addition to the base metal fatigue, it also contains the weld fatigue, which is the Verity approach plus the FKM capability, just to complete this. So I think we are pretty much at the end of the session. Our next webinar will take place on the 7th of November. We will talk about the parametric design study in this session. And I would like to close with a big thank you to all of our speakers of today. Thank you, Ankur. Thank you, Todd. Thank you, Mark. Thank you all guys for joining this session, and have a nice rest of the week. Thank you, and bye-bye.
Thank you, everybody. Also, thank you to Sagar for behind the scenes coordinating everything. Appreciate it.
Exactly, true, yeah. All right, so see you soon. Thank you, bye-bye.